Let's define the bell curve and see in what sense it represents a distribution. Here's the formula. The standard normal curve is defined by that formula. This letter is the Greek phi, lowercase phi. This is the most commonly used letter to describe this curve. And here you have a formula, and it is lovely. It's absolutely lovely. It has all the famous numbers of mathematics. It has e, it has pi, it has the square root of 2. It's just beautiful, and we won't use it at all. We will draw the picture, though. It's nice, though, to take a look at the formula and notice a few things. This, as a function of z, it's a function of z squared. So, for example, whatever value you get for z equals 2, you'll get exactly the same value for z equals minus 2. Whatever value you have for z equals 1, you'll get exactly the same for z equals minus 1. In other words, the function is symmetric about 0. Some of you will also have noticed that as z gets large, z squared gets large, whether z is negative or positive. As z gets large in the positive side, z squared gets large. As z gets large on the negative side, also z squared gets large. And then when you take a positive number and raise it to the minus power, that number starts to get small. So this graph is symmetric about 0, and it falls off symmetrically on both sides, and it looks like this. That's the bell curve, the standard normal curve. Centered at 0, falling off symmetrically on both sides. It's also a fact that the total area under this curve is 100%. So you can think of it as a continuous version of a histogram. And it's in that sense that it's a distribution. On the horizontal axis, what scale do we have? That's right, we have standard units. The center is 0, and this point, plus 1, happens to be the point of inflection of the curve. Those of you who know some calculus can do the exercise to find a point of inflection. You have to differentiate this function twice and see where it changes sign. The rest of you can just sort of see by eye that this is the point of inflection where it sort of going downwards cup to upwards cup. So what we have is an ideal of a distribution of a variable that has been measured in standard units. Of course, not all distributions look like this. Most distributions are skewed in one direction or the other, and they're not so regular, but some distributions come close. Not exactly, but close to this ideal. And why this particular curve as an ideal? Well, it occurs quite a lot, and it occurs quite a lot in various probabilistic settings that we'll talk about in just a moment. For now, let's see what proportions are in different ranges. So as we know, no matter what the shape of the distribution, Chebyshev's inequality says that the bulk are in the range average plus or minus few SDs. You really can't do better than that without knowing something about the distribution. If you happen to know that the distribution is normal, as if you draw the picture, you had a bell-shaped curve, then you can say quite a bit more. You can do much better than a bound. You can get an approximate value. If the histogram is bell-shaped, then almost all the data are going to be in the range average plus or minus 3 SDs. In general, you can say average plus or minus 5 SDs, but if the histogram is bell-shaped, then you know that you're going to capture pretty much everything in the range plus or minus 3 standard units. And you have approximations for other values of z. This table compares Chebyshev's bounds that are valid for all distributions with approximations for normal distributions. What percent of a distribution is in the range average plus or minus 1 SD? Well, Chebyshev for that wasn't really helpful at all. Chebyshev's bound is just at least 0%. If the distribution is normal, however, about 68%, just over 2/3, are in the range average plus or minus 1 SD. Because this curve is so well studied, these fractions have been calculated and approximated very closely. About 68% are in the range average plus or minus 1 SD, about 95% are in the range average plus or minus 2 SDs, and well over 99% are in the range average plus or minus 3 SDs if the distribution is normal. And it's that last line that allows us to say that if you've got a normal distribution, that pretty much everything is in the range average plus or minus 3 SDs. Note a couple of facts. These values here, these percents, are approximations, very, very good approximations. But they only apply when the distribution is normal. In general, all we can do are bounds. These approximations are consistent with the bounds. This number, 99.73, is indeed at least 88.888%. 95% is indeed at least 75%. But we're just much sharper. And why are we much sharper? Because we know the shape of the distribution. If you know the shape of the distribution, you can do very well when talking about what proportion is in which range. In a picture, this second line, average plus or minus 2 SDs, contains about 95% of a normal distribution. Looks something like this. We have drawn the distribution in standard units. No matter what the units are, whether you are measuring heights, weights, if the distribution is normal, then your curve is going to be like this, measured in standard units. The horizontal axis is going to have a 0 here, a 1 at a point of inflection. If you go 2 SDs on either side, you go from 0 to 1 to 2, and then from -1 to -2, so you pick up this interval. This gold area here is approximately 95%. The total area is 100%. It's a distribution. Take a look at this picture and cast your mind back to when you calculated confidence intervals based on bootstrapping sample means. Didn't your empirical distributions come out looking roughly bell-shaped? And it was under that condition that your percentile method for calculating confidence intervals applied. And what did you do? You picked off the middle 95% of the values. On the normal distribution, what you are picking off is center plus and minus 2 standard deviations of the curve.